Welcome to Tech Explained. Today, we're diving into Domain 8.
Okay.
Our goal today is to unpack secure software development and databases,
Right.
drawing from a couple of key resources you shared.
Right.
Think of this as your personal guide to understanding these crucial areas.
Right.
Cutting through the jargon to get to what really matters.
Yeah.
We'll explore how security becomes an integral part of building software from the ground up.
Okay.
And then we'll dive into the world of databases, looking at how they store and manage the information that powers our digital world.
Right.
One of the most striking takeaways right off the bat from these resources is this idea that security can't be an afterthought.
Yeah, definitely. When you go through these materials, it really hits you that it's not a separate feature you just tack on at the end. It's got to be baked into every single step.
Yeah, absolutely.
It's about ensuring that the applications we build, they can be trusted to protect that data.
Right.
The confidentiality, the integrity, the availability, the data, that's the core of any secure system.
Okay, so let's dig into this whole baking in security concept a bit more.
Sure.
One thing that really stuck out to me was how often security requirements are labeled as non-functional.
Yeah.
It's almost as if they're seen as these optional extras.
It's like saying, well, the house looks great. Who needs a lock on the door?
Exactly. And of course, when budgets get tight or deadlines loom, which, let's be honest, they always do,
Yeah.
these non-functional requirements are often the first to go.
They're seen as expendable.
It's penny wise and pound foolish because the resources make it crystal clear that trying to add security later on to retrofit it is way more expensive and far less effective than building it in from the beginning.
Think of it like trying to replace the foundation of a skyscraper after it's already built.
Yeah, a massive undertaking.
Not to mention risky.
Huge risk. So if we think about the entire lifespan of a system, what's called the system lifecycle, or SLC, it covers everything.
It really does. From that initial idea, the spark, all the way to its retirement and disposal.
Wow. And within that big picture of the SLC, we have the software development lifecycle, or SDLC.
That's right, focusing specifically on those development stages.
Got it. And why is that distinction important?
Because security concerns shouldn't just pop up during coding within that SDLC. It needs to be a guiding principle throughout the entire SLC, from the very first plan to how you get rid of that system and all its data.
So let's unpack the SDLC. Where do we even begin?
Well, it all starts with a plan, right?
Right.
Plan and management approval phase. We figure out the goals, the objectives, what problem are we trying to solve here, what outcomes do we want. We also start thinking about high-level cost estimates at this point.
Makes sense.
And probably the most important thing, getting management to say, yes, let's do this.
The green light.
It's the foundation, the very first step that sets the direction for everything else.
It makes you think, though, going back to your sources, how often do organizations really spell out their security objectives at this early stage?
That's a good point. The material suggests it might not be as common as we'd like.
Which can lead to problems down the road.
Absolutely. If security isn't a core objective from the get-go, it's a struggle to prioritize it later.
After planning, it's all about requirements, right?
Exactly. Here's where we get into the nitty-gritty. What do the users actually need this system to do? What kind of data are we dealing with? How does it fit into existing business processes? We gather all that, validate it, and turn it into a detailed set of requirements. This is where that abstract idea starts to take shape.
Okay. So at this requirement stage, security requirements also need to be treated just like any other functional requirement.
Absolutely. And they need to be specific, not just some vague statement like, the system should be secure.
Yeah, be more secure.
No, we need clear, measurable targets. For example, instead of saying user data must be protected, a much better requirement would be all personally identifiable information, or PII, must be encrypted at rest using AES 256 encryption and in transit using TLS 1.3.
So being super specific about the how.
Right. That gives clear guidance for the design and development teams later on.
Okay, I'm with you. And from those very specific requirements, we move into architecture and design.
That's it. We're taking those needs and turning them into the blueprint for the system.
The system's DNA.
Exactly. Detailed design documents outlining the architecture, the security controls, even things like screen layouts.
So it's all about defining how the system will function and, crucially, how it'll be secured.
Spot on.
Yeah.
This is where security starts to become real. You're going from abstract requirements to concrete mechanisms, technologies, even architectural choices.
Okay, so that brings us to the development phase. This is where the actual coding happens.
The rubber meets the road.
And from the resources, it looks like there are several different methodologies teams can use.
Right, right.
One that's mentioned is the Waterfall model.
Yeah, the classic.
It's described as a linear sequential approach. You plan everything out in detail, then you define all the requirements, then you build the entire system, followed by testing, and finally, the big release.
And the key thing with Waterfall is that you can't really easily go back to a previous phase. Like if you miss a crucial requirement halfway through a 2-year project,
You're stuck.
pretty much you have to see it through, then address that missed requirement in the next cycle. It's like water flowing downhill. It only goes one way.
Sounds pretty rigid.
It can be. Waterfall works best for projects with very stable, clearly defined requirements where you don't expect many changes.
Right, because the world never changes, right?
Well, in some cases, it might not.
Okay. But for those situations where things do change, which is most of the time, we have the Agile approach.
Yeah, Agile is all about adapting to change.
So it follows those same basic phases as Waterfall, plan, define, build, test, release.
But instead of doing them in a massive linear sequence, Agile breaks them down into short cycles, usually about 2 weeks each, called sprints.
So you're constantly cycling through, getting feedback, making adjustments as you go.
Exactly. It's perfect for projects where you expect those requirements to change, where you want to try out new ideas quickly, and where it's okay to fail fast, but fail within those contained sprints.
And how does that play into security?
Well, think about it. Those early, frequent feedback loops mean security issues can be caught much earlier.
2 weeks instead of 2 years down the line.
Precisely.
Agile also brings in this role of the Scrum Master. What exactly do they do?
The Scrum Master is like a facilitator for the team.
Not a manager.
Not in the traditional sense. They're more like a coach, making sure the team is communicating well, working effectively, and removing any obstacles that might slow them down.
And are security concerns part of those obstacles?
Absolutely. A good Scrum Master will make sure security is a regular topic of discussion and is addressed in each sprint.
Okay, so we've got Waterfall and Agile. What's next?
DevOps. This one is all about speed and efficiency.
How so?
It combines development, quality assessment, and IT operations into one streamlined process.
Streamlined for what?
To shorten the development lifecycle, we're talking daily releases of new code or features, sometimes even more frequent.
Wow, that's fast. How do they manage that?
DevOps heavily relies on automation. Practices like continuous integration, where code changes are constantly merged into a central repository,
Okay,
and continuous delivery, where those changes are automatically prepped for release.
makes sense. Now this brings us to an interesting point. SecDevOps. How do you integrate security into this super fast DevOps world?
That's the challenge, right? You have this need for speed and agility, and traditionally security practices have been seen as slowing things down.
Yeah, like that whole separation of duties thing.
Exactly. But with SecDevOps, it's about finding that balance. It's about shifting security left, integrating it early and continuously. We're talking strong collaboration between development and security teams, adopting secure coding practices, and using automated security testing throughout.
Got it. So we've gone through planning, requirements, architecture, development. What's next in the SDLC?
Testing. And I can't stress enough how important it is to test throughout the entire life cycle.
Not just at the end.
No. We're talking validating requirements, reviewing designs, unit testing, interface testing, integration testing, and even system testing.
Whoa, a lot of testing.
It's essential. And we can't forget about testing during operation as well.
Okay, one specific testing technique that came up was canary deployments. What are those all about?
Think of it like a canary in a coal mine. You release new features to a small group of users first.
Like a test group.
Exactly. It's an early warning system to see if anything breaks before you release it to everyone.
Smart. Minimize the damage if something goes wrong.
That's the idea.
So after all that testing, we move on to certification and accreditation.
Yes. And remember the evaluation criteria we talked about in Domain 3.
Vaguely.
All right, so certification is a technical analysis of an IT solution.
Yeah.
It's making sure it meets those security requirements. And in the SDLC, this fits under the testing phase.
Okay, the techie stuff.
Right. Accreditation, on the other hand, is the official management sign-off on that certification.
So the bosses say, okay, we accept the risk.
For a specific period, yes. And this usually falls under the deployment phase.
Makes sense. So once a system is certified and accredited, we're ready for deployment, right?
That's right. We're moving it into the live environment.
It's go time.
And this requires careful planning too. Secure configuration of the environment, access controls, robust monitoring. These are all crucial during deployment.
All right, so now the system is up and running. We're in the operation phase of the SLC.
And security is still vital here. Continuous monitoring, regular security assessments, applying patches, having incident response procedures, these need to be ongoing activities.
Can't just set it and forget it.
Definitely not.
Yeah.
Systems need to be actively managed and protected throughout their operational life.
Finally, we reach the disposal phase. It seems like this stage often gets overlooked.
It does, but it's critical. When a system is retired or replaced, you need to think about migrating data, archiving what needs to be kept, and securely destroying what doesn't.
Especially with all the data privacy regulations these days.
Right. Improper disposal can lead to serious breaches. It's not just deleting files. Sometimes it means physically destroying storage media to ensure that data is truly gone.
Okay, so we've covered the entire SLC. Let's shift gears a bit and talk about maturity models.
Right.
Your sources describe them as tools for evaluating and benchmarking organizational processes. How well defined are they? How consistently are they applied?
And there's this common 5-level model.
Yeah, what's that all about?
Level 1, initial, is basically controlled chaos. No real defined processes. As organizations mature, they move through level 2, repeatable, where there are basic processes but maybe not well documented.
Right.
Then level 3, defined, where processes are documented and standardized.
Got it.
Level 4, managed, where those processes are measured and monitored.
So you're tracking how well they're working.
Exactly. And finally, level 5, optimized, where the focus is on continuous improvement.
Sounds like a lot of work to get to that top level.
It is. And honestly, it's not always practical or even necessary for every organization.
Makes sense. So it's more about using this model as a benchmark for improvement.
That's the key takeaway.
Okay, let's move on to something a bit more technical. Application programming interfaces, or APIs.
Yes. APIs, the glue that holds the internet together.
Really?
Well, they're definitely essential. They're what allows different applications to communicate with each other.
Give me an example.
Say you're using an app on your phone to book a flight. That app is likely using an API to talk to the airline's servers, retrieve flight information, and make the booking.
So it's like a messenger between applications.
Exactly. And the great thing about APIs is that they let developers reuse complex functionalities without having to write all the code from scratch every time.
Saves a lot of time and effort.
A huge amount. Now, there are different ways to build APIs. 2 common ones are REST and SOAP.
Okay, tell me about those.
REST, or Representational State Transfer, is the most popular right now. It's known for being lightweight and fast.
So good for web applications.
Perfect for them.
Yeah.
SOAP, on the other hand, is more traditional, but more complex, but offers a wider range of features.
Web horses for courses.
Exactly. And of course, security is a big consideration with APIs as well.
How so?
We need to make sure that applications are authenticating themselves properly, that they're only authorized to perform certain actions, and that the API itself is protected against common web application vulnerabilities.
Just like with any other software. Okay, let's talk about something a little bit more obscure. Code obfuscation. What is that?
Imagine you have this valuable source code.
Right.
You want to make it really hard for someone to reverse engineer it to understand how it works.
Like protecting your secret recipe.
Exactly.
Yeah.
So you use code obfuscation to transform that code into something that's much harder for humans to read and understand while still allowing the computer to execute it.
So it's still functional, just harder to decipher.
Exactly. And there are different ways to obfuscate code. You can change the formatting, rename variables to meaningless names, even make the program's logic more convoluted.
It's like scrambling a message.
That's a good analogy.
Okay, so that's code obfuscation. What about acquiring software securely?
This is all about ensuring that the software you bring into your organization, whether it's custom built or off the shelf, is free from vulnerabilities and will function as intended.
So you're not introducing any new security risks.
Exactly. And a big part of that is assessing the security practices of your software vendors. Do they follow secure coding principles? Do they have a good track record?
And contracts and SLAs come into play here, right?
Absolutely. They can be used to define specific security controls that the vendor must have in place, as well as mechanisms for monitoring and reporting on their effectiveness.
It's like having a security checklist for your vendors.
Exactly.
Now let's dive into some of the common software security weaknesses and vulnerabilities.
All right, let's get specific.
First up, we have buffer overflows. Explain those to me.
Imagine you have a container, a buffer in memory.
Okay.
And you try to pour more data into it than it can hold.
What happens?
That excess data spills over, potentially overwriting important information or even code nearby.
And that can be exploited by an attacker.
Absolutely. They could potentially inject their own malicious code.
How do you prevent that?
Through techniques like parameter and bounds checking, making sure you never write more data than a buffer can handle.
Okay, so you're being careful about how much you're putting in.
Right. And there's also ASLR, address space layout randomization. It randomizes where things are stored in memory, making it harder for attackers to target specific locations.
Like shuffling a deck of cards.
Exactly.
Next up, we have SQL Injection. Now, we've touched on this before.
Yeah, a classic and unfortunately still very relevant attack.
It's where an attacker inserts malicious SQL code into a web application, and that code then gets passed on to the database.
And if the application isn't careful, that malicious code could allow the attacker to control the database.
Steal data, modify data, delete data. Bad news.
Very bad news.
And how do we prevent this?
Rigorous input validation. Never trust user input. You need to carefully check and sanitize any data that's coming from an external source before using it in a SQL query.
Okay, so you're essentially filtering out anything that looks suspicious.
Exactly.
Moving on, we have cross-site scripting, or XS.
Another common web application vulnerability.
This one involves injecting malicious scripts, usually JavaScript, into web pages that are viewed by other users.
And when those users load the page, the attacker script gets executed in their browser.
So it's targeting the user's browser directly.
That's the goal. It could be used to steal information, redirect users to malicious websites, or even take control of their accounts.
And there are different types of XSS attacks, right?
Yes. There's stored XSS, where the malicious script is permanently stored on the server, and reflected XSS, where it's injected into a request and then reflected back to the user.
Okay. Now, XSS targets the browser. What about cross-site request forgery, or CSRF?
CSRF is a bit different. This one targets the web application itself.
How so?
The attacker tricks a user into sending a malicious request to the web application.
Without the user even knowing.
Exactly. It often exploits the trust that the application has in the user's browser.
So the application thinks the request is coming from a legitimate user and carries it out.
Right. It could be something like changing an email address, transferring funds, or even making purchases without the user's authorization.
Sneaky.
Very sneaky.
Next on our list, covert channels. What are those?
These are unintended communication pathways that can be used to leak information.
Like a hidden tunnel.
Kind of. It could be something as simple as one process modifying a file in a specific way to signal information to another process.
Ah, so it's not using the intended communication channel.
Right. It's exploiting something else, something that might not even be obvious.
And these are hard to detect, I imagine.
Very hard. And even harder to eliminate completely.
Okay. What about backdoors or trapdoors?
These are intentional entry points that are put into a system to bypass security controls.
So someone intentionally creates a way to get in without going through the front door?
Exactly. It could be a developer who puts it in during development, or an attacker who exploits a vulnerability to insert a backdoor later on.
And that gives them persistent access, I assume.
Most likely. They can come and go as they please, without having to authenticate each time.
Definitely a major security risk.
A huge risk.
Memory reuse. What's that all about?
It has to do with how memory is managed. When an application finishes using a portion of memory, it releases it back to the operating system.
Okay.
But sometimes, that memory might still contain sensitive data from the previous application.
So like leaving your notes behind in a classroom?
Kind of. And if the operating system doesn't properly clear that memory before giving it to another application.
That second application might be able to access the old data.
Exactly. It's like finding someone else's diary.
Not good.
Not good at all.
What about TOCO or race conditions?
This is a bit tricky. Imagine an application checks the state of a resource, like a file, before it uses it.
Right.
But between the check and the use, the state of that resource changes.
And the application is using outdated information.
Exactly. An attacker could potentially exploit this by manipulating the resource in that small window of time.
So it's a race against time.
Exactly.
Finally, we have citizen developers. What's that all about?
This is a growing trend where business users are creating their own applications using these new low-code or no-code development tools.
So they don't need traditional programming skills.
Right. Which can be great for empowering users and driving innovation.
Nice.
There's always a but. These citizen developers often lack formal training in secure coding practices.
So their applications might have vulnerabilities.
Exactly. It's important for organizations to provide guidance and oversight to ensure those applications are secure.
Okay, so we've talked about a lot of vulnerabilities. Let's switch gears again and talk about some secure programming techniques.
Right.
One that keeps coming up is input validation.
The cornerstone of secure coding.
It's about making sure that any data that enters an application, especially from external sources, is what you expect it to be.
Right. You need to check both the format and the actual values of the data.
So you're essentially filtering out anything that's malformed or potentially malicious.
Exactly.
Another important technique is session management.
This is all about managing a user's interaction with an application after they've logged in.
So it's keeping their sessions secure.
That's the goal. Things like preventing multiple logins, using strong session IDs, enforcing timeouts, and using screensavers to automatically log out inactive users.
Okay, so you're making it harder for someone to hijack a user's session.
Exactly.
And finally, we have polyinstantiation. This one sounds a bit more complicated.
It is. It's a technique that allows different versions of the same data to exist at different security levels.
Give me an example.
Say you have a database with confidential and secret information. A user with confidential clearance might see a record with certain information, while a user with secret clearance would see a different version of that same record with more sensitive information.
So it's like showing different views of the same data based on the user's clearance level.
Exactly. It helps prevent unauthorized inference.
Okay. Now, your sources also briefly mention maintaining software in operation.
Right. Keeping those systems secure over time.
They mention SCM tools. What are those?
SCM stands for Software Configuration Management. These tools are used to track and control changes to software code.
So you have a record of every modification.
Exactly. It's important for accountability and for being able to roll back to previous versions if necessary.
And they also mention SOAR software.
SOAR stands for Security Orchestration, Automation, and Response.
What does that do?
It helps automate a lot of the tasks involved in security operations. Things like threat and vulnerability management, incident response, and security policy enforcement.
So it's like having a security robot that helps you manage things.
Kind of. It takes care of a lot of the repetitive tasks, freeing up security teams to focus on more strategic work.
Okay, let's move on to our final topic, databases. What exactly is a database?
In the simplest terms, it's an organized collection of data, usually structured in tables with rows and columns.
Like a spreadsheet?
Similar, but much more powerful. We're mainly talking about relational databases here, where data in different tables can be linked together based on defined relationships.
Okay, so it's all about organizing and connecting data.
Right, and that makes it really efficient to store, access, and analyze large amounts of information.
And at the heart of any database system is the database management system, or DBMS.
The DBMS is the software that lets you interact with and control the database. It handles all the underlying technical stuff.
Like a database operating system.
You could think of it that way. Now, the resources break down a DBMS into several key components.
Okay, what are those?
First, you have the hardware, the physical servers that store and process the data.
Right.
Then there's the software, the operating system, and the DBMS software itself.
Like MySQL or Oracle.
Exactly. And then you have the database itself, which can contain one or more tables.
Okay.
Each table is structured into rows, which represent individual records, and columns, which hold specific pieces of information about those records.
Makes sense.
And then you have primary keys, which uniquely identify each row, and foreign keys, which link data in one table to another.
So it's all about relationships.
Exactly. And the language we use to talk to the DBMS is usually SQL, or structured query language.
The language of databases.
You got it. And of course, we have the users, the people or applications that use the database, and the data itself, the information stored within.
Okay, so that's the anatomy of a DBMS. Now, what about maintaining the integrity of data?
Data integrity is absolutely crucial. If the data in a database is inaccurate or inconsistent, it's basically useless.
Right.
So databases have a lot of mechanisms to make sure the data stays accurate.
Like what?
One challenge is concurrency. Multiple users or applications might be trying to access and modify data at the same time.
Leading to conflicts.
Exactly. So databases use locks to prevent one transaction from interfering with another.
So only one person can change a piece of data at a time.
That's the idea.
And then there are the ACID properties. What are those all about?
ACID stands for atomicity, consistency, isolation, and durability.
Okay, break those down for me.
Atomicity means that a transaction is treated as a single unit. Either all the changes happen or none of them do.
Okay.
Consistency ensures that any changes maintain the integrity of the data.
So no invalid data gets in.
Right. Isolation means that transactions are isolated from each other so they don't interfere.
Like separate workspaces.
Exactly. And durability means that once a transaction is committed, those changes are permanent,
They're saved for good.
even if the system crashes.
Wow, those are some powerful properties.
They are the foundation of reliable database operations.
And finally, we come back to SQL injection. This vulnerability just keeps popping up.
It's a persistent threat, and it highlights how important it is to secure not just the database itself, but also the applications that interact with it.
Right, because a vulnerability in an application can give an attacker a backdoor into the database.
Exactly.
So, as we wrap up this deep dive into secure software development and database security,
What are your main takeaways?
well, I think the biggest one is that security can't be an afterthought.
It's got to be a part of the process from day one.
From that initial plan, through all the development phases, and even into operation and disposal.
And the second big takeaway is that secure software development and database security are deeply interconnected.
You can't have one without the other.
Right. If you have vulnerabilities in your applications, your database is at risk. And if your database isn't secure, your applications are vulnerable.
It's like building a house. You need a strong foundation, secure walls, and a good roof to protect everything inside.
Exactly. And just like you wouldn't build a house without locks and security systems.
You shouldn't build software without considering security at every step.
And as our reliance on software and data continues to grow, these principles are becoming more and more important.
It's not just about protecting organizations anymore. It's about protecting individuals and society as a whole.
Exactly. So as you continue to explore this domain, think about how you can apply these concepts in your own work.
Whether you're a developer, a security professional, or just someone who uses technology every day.
Because understanding these principles can help you make informed decisions and stay ahead of the ever-evolving security landscape.
That's a great point to end on. Thanks for taking this deep dive with me.
You got it.
Until next time.